last time we looked at this. Uh, behavior, irrational prime in Z Gaussian integers. And here's what we got. One of two things happen. Number one, if P was equivalent to 3 mod 4, then P is still prime. So it got to keep its status, right? It was still prime. Number two, if P was equivalent to 1 mod 4, then P was equal to alpha beta, where alpha, beta were distinct primes. Yeah, the Gaussian. That was the second thing that happened. And the only thing left is P is 2. Right? 2 was equal to 1 plus I over squared. So in other words, 2 was kind of strange because it was actually it was the perfect power. 1 plus I is actually a prime here. It's got norm 2 in here. And up to a unit, because negative I is a unit, 2 was the square. So let me give you kind of something here. This is kind of yes.
What do you mean by a rational?
A prime that is in the rational numbers, like an ordinary integer prime.
I guess I'm confused why you're not saying integer prime.
Tradition, you know, basically that's kind of it. So,
also tells you that the integral closure of C and C is just itself.
Like, yeah, that's right. Yeah, that's true of any actual UFD is integral closeness. Well, following theorem. This is generalizable, and so this is kind of a warm up. This is sort of similar to a theorem we'll get to later. Let R the ring of integers of field Q radical n, where P is squared. Then P this remains prime in R if and only if yeah, so I'm gonna do it this way. Then the odd prime P remains prime in R if and only if dP is -1. So if you have an odd prime, if the symbol we used right here was -1, because I is -1 squared. So take generally dP, you get -1 from the symbol, and the proof is almost exactly like our example. You might ask, well, what happens? What happens with 2? 2 is a special case, And it depends heavily on whether D is equivalent to 1 mod 4 or not. And we'll look at that as here. But basically, again, the behavior of P in this quadratic extension, whether it remains prime or whether it breaks down in some fashion, depends on the symbol here. I'm going to do one more UFD example, and then I'm going to do one that's not UFD. We'll see some interesting stuff that happens. So, next example. And again, I'm gonna take advantage of the fact it turns out that this is a UFD. I'm gonna take advantage of this fact for this example here, and then I'm gonna do examples of UFD and see if we can kind of figure out what's going on. Okay, well, a typical element again, you multiply this by its conjugate in this case, complex conjugate, you get a squared. Notice that just like the Gaussian integers, you can use the same easy argument and show that this norm is multiplicative. That is, the norm of alpha beta is the norm of alpha times the norm of beta, and all those properties that these always work. Now, which primes break up? Well, let's suppose that P is odd. So how do we determine? Well, if I believe this theorem, then P remains prime if and only if the symbol and of course here the role of D is -2. So basically what we're doing is we're sniffing around and saying, okay, for which primes P is -2, not a squared mod, right? That's what we're hunting for, right? So how do we analyze this? Well, now, as I recall, there's that. Anybody remember what it was for 2P? Plus or minus 1 mod. Yeah. 1,7 mod A, which is exactly what it said. Now, of course, at the end of the day, this has to be -1, right? So what can we conclude? Or actually the other way around, right? If we're looking for this, right? So we need four minus 2p equals 1. That's what we need to have, right? So this is going to be determined mod what? It's going to be determined mod 8, right? Because let's do this, case 1. That's one way this could happen. So what does that give us? That gives us that P is equivalent to 3 mod 4. No, my bad. 1 mod 4. And P is also equivalent to 3 or 5 mod 8. Agree. So in the first case, this must happen. So what can I conclude from this? Right, so it must be the case you are, mod 8 determines mod 4, right? So 3 mod 8 is never 1 mod 4. That can't happen at all, correct? But 5 mod 8 is always 1 mod 4. So second case, let's have P is equivalent to -1 mod 4, and P is equivalent to 1/7 mod 8. Actually, let me 3 mod 4 is the same thing. Notice if you're 7 mod 8, then you're 3 mod 4, but if you're 1 mod 8, you're negative. So you got to conclude P is equivalent to 7 mod 8. Right. So we can break it down as follows. We have minus 2p is equal to -1 if p is equivalent to 5 or 7 mod 8, and 1 if p is equivalent to 1 or 3 mod 8. And so P remains prime if P is equivalent to 5 or 7 mod 8, and P equals, this is very much like the Gaussian integers. It breaks down into 2 pieces here. With norm alpha, norm beta equal to P if P is equivalent to 1 over 3 mod 8. So actually a consequence of all this is, did y'all figure this out over your smashing weekend, that if P is equivalent to 1 or 3 mod 8, then P, you can write P as a square plus twice a square. because that's what the norm of that out should be, right? I mean, just for giggles, let's pick one. What's one? 17, right? 17 is equivalent to 1 mod 8. Anybody see how to do it? Magic, right? 3, let's see. What's a good one? 43 is equivalent to 3 mod 8. I've already got what was it? 3 squared? It was 18.5 squared. And that's an infinite, right? I mean, that's a little bit of number theory magic, and it comes from the way that these decompose in this UFD. I guarantee you, any prime equivalent to 1 or 3 mod 8 can be decomposed into a square plus twice a square. Okay. Pretty interesting, right? Let's do one that's a little bit more on the dark side. Example. This is this everybody's first example of a non-UFD? How many of you, this was your first, right? I mean, this shows up in like almost every algebra book. And they make you go through a little bit of machinations, right? They take 6 as 2 times 3, and then it's 1 plus radical negative 5, 1 minus radical 5. Let's look at this one, shall we? This one is not a UFD. So something's going to be a little bit different, and it's probably going to pop up here, right? Because if something remains prime, then good for it, right? But if one of these rational primes breaks down, well, maybe it breaks down into smaller irreducibles, perhaps, or maybe not. And we'll look at what can happen. The first thing I want to do is I want to ask myself this: self, which primes remain? So that's the first order of business. Well, in this case, oh, by the way, I forgot to do it back in this one here. I did a pretty good coverage of the odd primes. What happens to the prime 2 here? Again, 2 is a square. Up to the unit, it's a square of 2. Here I'm going to start with P big odd here, just like I did before. Well, P remains prime if and only if symbol minus 5P is minus 1. Right. That is to say, negative 5 is not a square of 1. So, or mod P. So you can do a very similar analysis, and you might, maybe I'll ask you something like square root of negative 30, right? Which is a pain in the butt on homework because you've got 2, 3, and 5, and you don't have to break that up, but it's all good. So so the analysis of this one is similar to the previous one in the sense that to get negative 1, this is either got to be 1 minus 1 or minus 1, right? I want this to be 1. So is equal to 1 if P is equivalent to 1 mod 4. And it is equivalent to -1 if P is equivalent to 3 mod 4. Again. But what about the other symbol? This one's a little bit more obnoxious, right? So let me compute the other symbol over here and see what we get. I need to know if this symbol is 1 or negative, right? So what do you prescribe here? Come on, give me a little reciprocity here. How about that? Let's do. Whoops. Okay, so there's quadratic reciprocity. I get a little lucky here. That's kind of sweet because this one's the E, right? Which means that the whole exponent is even. So this is just P5. So reciprocity doesn't induce any minus signs. So actually, I guess we can figure this out. Now the question is just when is the prime P? Well, what square is mod 5, basically? So mod 5, well, I guess we're going to get 0, can't we? 1, 4, 4, 1. So what's my outcome here? It's 1 minus 1. One if it's what, 1 or 4 mod 5, and -1 if it's 2 or 3 mod 5, right? So let's record that over here. By the way, this should be determined mod what? Agreed. This should be determined mod 20, right? And actually, we're going to see how many. So I always like to think about this problem before I do it. So how many equivalence classes should I have if I've covered everything relatively prime to 5 and 2? And there should be 8, shouldn't there? Right? Because it should be the Euler phi function of 20, which is, I believe, 2 times 4, 9. So there should be 8 cosets that are relatively prime to 20, right? And we should see those 8 coming up in here, right? And I notice that since we're combining, what are we going to get -1? We're going to have 1, -1, or -1, 1. And if you look at all the possibilities, it looks like there's 2, 4, 6, 8. It looks like there should be 8 things coming out of this, right? So there's a lot of stuff that's like really tying the room together here. So let's case 1. Let's suppose that -1p is equal to 1 and 5p is -1. So that is to say P is equivalent to 1 mod 4, and P is equivalent to 2 or 3 mod. So this is kind of Chinese remainder theorem. I need solutions mod 20. Oh, thank you. Yes. Here, that's correct. And these are, yeah.
I don't think the other one has any solution.
So, what do we got here? So if you're 2 mod 5, let's go through that. You know, I like to be simple-minded here. I'm just going to go through 2 mod 5 until I hit one that's equivalent to 1 mod 4. So 2 doesn't work, 7 doesn't work, 12 doesn't work. But now we got 17. 17 is equivalent to 1 mod 4. So 17 is one of them. Now I've got P is equivalent to 3 mod 5, and it's got to be 1 mod 4. So 3 doesn't work, but 13 does. So the Chinese remainder theorem should give, so you got the 1-2 case and the 1-3 case. Chinese remainder theorem says that there should be one and only one solution, mod 20. And once I found it, I'm good to go, right? Case 2. So this time I get P is equivalent to 3 mod 4. And P is equivalent to 1-4 mod 5. Again, the Chinese remainder theorem, all I got to do is plug along until I get a solution. So 1 mod 5, well, so 1 doesn't work. 6, oh, that's even, that's not going to work. So let's just add it to 10s. 1, 11, 11 works. Now let's go 4 mod 5. 4 is even, so let's go to 9. 9 doesn't work. 19 does work. And there's my 4 with -1. The other 4 cosets, actually in this case, well, it's not a coincidence, but it turns out the other cosets are the negatives of this. So let me kind of summarize this here. $11, $13, $17, $19, mod 20. And 1, if B is equivalent to 1, 3, 7, or 9. So notice that we've run through all the primes that are now relatively prime 20, right? Because these are precisely the 8 cosets that are relatively prime 20. What primes are all sad and out and cold now? 2 and 5. Yeah, we already looked 2 out in the cold, right? And of course, 2 is not going to show up in any of these cosets. And 5 is also problematic. So 2 and 5, we're going to put a question mark there for so in this case,
are they ramified?
Yes, yeah, that's exactly what happens. And we're going to see they actually kind of ramify in different ways. Here, these remain prime. And here, I'm going to use the unprofessional terminology, break down. And I'm going to try to show you ways that this can happen. Well, so for right now, you can think of breakdown meaning, okay, these ones have all been demoted, they've lost their prime status in Z adjoint with square root of -5. And then also, we've got our rows here.
Is term breakdown like good reduction?
Yeah, it reduces in some sense, right? So let me give you kind of a problem here. Notice, look at 3. So I'm going to ignore the primes that are that remain prime, right? Because that's pretty clear what happens. They're just still primes. 3 is one of the ones on my breakdown list, right? But it doesn't break down in the sense that you're used to. Look at 3, and let's look at yeah. So let's look at 3 and maybe 29. Yeah, let's look at 3 and 29. These are both on the breakdown list, right? 3 comes out of here, 9 comes out of here. 3. Now, notice that if a plus b square root of -5 is in C adjoint square root of -5, then the norm value right. Notice that the way 29 breaks down is fairly straightforward once you see it, because you actually can write 29 as a square plus 5 times a square, right? All you have to do is let b be 2, that's 20, and a be 3. So and what this means is 29 is 3 plus 2 radical -5, 3 minus 2. Right? And we're all feeling pretty good about this because I said that 29 should break down. And there you go. It's factored into 2 things that are smaller in some sense. This doesn't happen for 3, does it? Right? Because, but if 3 is alpha beta, then the norm of 3 is the norm of alpha, norm of beta. And in this particular situation, what you have is 9 is now for 3 to break down in a non-trivial sense, neither one of these has to or can be 1, right? So these have to be, neither one of these can be 1, nor can they be 9, right? So the only way that you can break this down is for norm alpha and norm beta to both be 3. Can't happen. All right. So actually, that's kind of interesting because 29, one of our breakdown primes, actually reduces. 3, another one of our breakdown primes, does not reduce. Or does and it doesn't as an element, but as an ideal, it does. So let me make the following observation. Consider ideal consider the smallest ideal that contains 3 and 1 plus radical -5. This is an ideal in this room, right? What's the first thing I should probably convince you about? What would it be proper for me to do right now? Yeah, I should probably convince you that this is really an ideal that, you know, is proper. And you know what? I'm not going to do it because I'm going to do it. It's going to come up, right? This is an ideal, certainly. It may be the whole ring, right? But it's not. Let's look at this idea. And I hope my notation suggests it, because this is, in a certain sense, is a complex conjugate of this idea, right? It's everything generated by 3 in the conjugate of. By the way, let me point out that both the ideal generated by 3 is contained in both of these because after all, they both have the element 3 in them. Right? I agree with that. Now consider this ideal here, product. Well, the product of any pair of ideals, if they're finitely generated, is generated by all the products of the generators, right? So this is by the way, how many generators do you expect the product of these two ideals to have? Right. You were very careful with the language here. In general, I would expect, I mean, if you have like, generally speaking, I expect there to be 4, right? For example, if you have, and I hope we all remember this, take a polynomial ring in 4 variables and you multiply these ideals, this is certainly generated by xz, xw, yz, yw. And it's fairly easy to show that that's as good as it gets as far as the economics, right? You can't really generate this less, right? I expect when you multiply generator for you to need all possible products. This one goes from being 2 generated ideal to 2 generated ideal. Product is a principal ideal, which is bananas, right? So let's see why this is true. Products of all the generators. Well, we've got 9. We've got 3 minus 3 radical negative 5. We've got 3 plus 3 radical negative 5. And then we've got this product here, which I guess is 6, is it not? So this new ideal, PP bar, is generated by these 4 things. Now, the first observation that I'm going to make about these 4 things is certainly this product is actually contained in the ideal generated by 3. Why is that? Because every distinct generator is divisible by 3. So 3 contains that. Right? And when I say the ideal generated by 3, I mean the ideal generated in this array. Right? But the other containments too are true as well. Does anybody see why?
Add the 2 in the middle, or you can subtract 9 and 6.
Okay, that's what I would do. I would take 9 minus 6. You've got this minus this equals 3. And so you actually get this containment as well, right? And so you have equality. So actually, P times P bar is equal to the ideal generated about 3 is principal. Now, the first observation is somebody now argued for me that P is in fact a proper ideal.
If it weren't, then 3 would be P bar, but 1 minus square root of -5 is not equal to 3.
Right. If P were proper, it contains 1. There's some linear combination that contains 1, right? The complex conjugate of 1 is 1. So 1 would also be in P bar, right? And so it would have to be in the product, right? So there you go. All right, so this is a product of two proper ideals that are not generated. I guess the next thing, really, if I'm super careful, is you might say, oh, Jim, you might have pulled a fast one here, right? Because maybe this is generated by a single element, alpha, and this is generated by a single element. So maybe it's not so surprising these might be two principal ideals, but they're not. Can somebody tell me why it's impossible for those two principles? Suppose, for example, right? So suppose, for example, that suppose that one suppose that it's generated by a single element alpha. I shouldn't have this, shouldn't I? This means that alpha divides 3 and alpha divides 1 plus radical -5. Correct. So the norm of alpha should divide 9, and the norm of alpha should divide 6, because the norm of this is 9 and the norm of this is 6, right? The norm of multiplicative has to divide it. Everybody okay with it? Well, so that means that the norm of alpha is a common divisor of 9 and 6. So the norm of alpha must divide GCD. See, those homework were important after all, weren't they? So norm of alpha must divide GCD of 6 and 9, which is 3. So your only choice for the norm of alpha is 3 and 1. 3 is ridiculous because you can't write 3 as a square equals 5 times a square. And 1 is impossible. But what happens if the norm of alpha is 1? That's right. If the norm of alpha is 1, that means alpha is a unit, which means that the ideal P was the whole thing, right? Which is awesome. So this is actually a bona fide example here. Everybody okay with that? Okay, so let me give you sort of one last theorem. I'm gonna do a little bit of computation. All right, so here it is. So now what we have is we have in this ring, we've seen that you've got several things can happen. Number one, you have one several in this case. I mean, could be 3 and 5, depending on how you argue. Number one, 2P. Number one, P remains prime. Number two, P equals alpha beta with norm alpha, norm beta equal to P. Actually, what happens here is P actually decomposes into 2 prime elements. 2 or 3 The ideal generated by 3 is P1 or is P bar. This doesn't just work for 3, this happens for other primes where it doesn't, where if P is one of our breakdown primes and it doesn't do this, it has to do this. Right? And there's 2 more. There's 5 and 2. And this behaves like this one, only just a little bit different. Well, Jim, what do you mean by different? So you should check this actually, just for fun, that this ideal right here times this ideal is 2. It's very much like this. But you might say to yourself, is Jim having a stroke? Why is this different than 3? He might tell me what the subtle difference is.
They're the same idea.
That is correct. As opposed to this case right here that we have with P, the conjugate in this case is actually the same ideal. So this is 2, 1 plus radical negative 5 squared. And that's the only case where the conjugate is equal to itself. Well, besides negative 5. Okay. Any questions on that? Okay, I'm going to give you a big theorem tomorrow. We're going to do some computations that are beyond quadratic, and then we'll move on to integral. Any questions? All right. Y'all have a good one. Don't forget that today is Monday, so I'll have a meeting at 1, but you can holler at me and talk to me before that.